And lot of indigenization work also she has taken up and won around 6 numbers of Impress Awards. And she has done module engineering to a great extent for both Max, Valmet, and NPCIL jobs, which is recently handled by BHEL. And NPCIL engineering also she has taken up, and she is more specialist in our processor modules. So these are the processor modules which you will be encountering a lot of problems in sites because processor, as you know, is the brain of the system. So when processor goes bad, a lot of our field processes get stuck, in which case all our engineers will be in trouble. So whatever queries you have and whatever problems you are encountering in your sites, you may please discuss with her, and you may please store those questions for the end of the session. And in case you feel that it is to be clarified, then immediately you may unmute yourself and ask also, or you can post it across the chat box. Kindly post it to everyone. Please don't put a chat on the chat box to privately to faculty. This is our request because both question and answer are known by all the participants who are online. So it is more advantageous. So other person may also have the similar question. So when you are posting a question on chat box, kindly post it in public. That is in everyone. That head only you post. And one more very humble request is people are leaving the site without even entering the feedback. So this is a 3-digit number followed by 2 slashes and your name. This is all we want. Kindly enter your name followed by 54321 digits. 5 stands for highest. First digit is for the faculty rating, followed by a slash. Again 54321 rating. That digit stands for the coordination. Again followed by a slash 54321, which stands for the WebEx tool rating. This tool rating is also important to us because whether we should continue with the same tool, we have to decide. So kindly don't leave the site without entering your feedbacks, which is very, very valuable to us. This is our humble request. And please stay online. For now, to Sujama. Sujama, please take over. I'm giving the host rights to you.
Okay, thank you, Padma ma'am. Am I audible? Yeah. Thank you, Padma ma'am. So I'll just take over.
Welcome. I'm muting myself, and kindly all of you mute yourselves.
So good afternoon to all of you. This is Suja. In this session, we will be handling all the I/O cards, that is analog I/O modules, mounting boards, and IBC, IPSP, and cross connection boards. So these are the set of modules which we will be discussing in this session. First slide, what you're seeing is you are able to see the slide, no? I'm sharing. Yeah. So MBM 120, that is mounting board for IBC and IPSP. So you can see here this two modules, that is IBC and IPSP, can be mounted onto this MBM 120. So this left side rectangle, what is marked here, this is the place where IPSP will be housed. And then right side, this is the place where IBC will be housed. So here, if you see, basically this mounting board will give the path for power and data for both IO groups. And you can see here switches, that is S2 is for FBC address and S1 is for IBC address. And then two socket mounted fuses are there. So this F1 fuse is monitored by IPSP. See, basically here we will be connecting 24 volts input. This X8 what we are seeing here, this is the input point for IPSP. So this incoming 24 volts is passed inside IPSP after F1. And further, the same 24 volts, incoming 24 volts, it's fused through F2, and then this will be made available in the side connector X4. So through which all analog IO modules and digital output modules will get the power supply, which will be used only for field side circuitry inside the module. That is the idea. And here there are two slide switches, that is S3. These are loop control switches. This will be used to enable module to send fault signal in case of no proper connection between X13. X13 is the place where we will connect interlink cable. And then also the incoming fuse, that is 24 volts, is falling below 21 volts also. That will be raising one fault. So what you see here is X12, this Ethernet connector. This is where the data redundancy is taking place between two IBCs. And this is the place, X13 is the place where we will get the power supply redundancy. IPSP basically converts the incoming 24 volts to 5 volts output. That 5 volts will be available in X13, and then through the interlink cable it is passed on to the adjacent mounting board. So this is for the redundancy path for power supply, and this is the redundancy path for data. And this connector, what you are seeing here is X3. This is the side connector which will be connecting to module IO modules mounting board, that is called MBI8, and X3 carries all the system side signals including plus 5 volts, whereas X4 will be carrying the field 24 volts after F2. Incoming 24 after F2 directly it will be available here, and module will be taking the power from this and then generates its own circuitry and things like that inside the IO modules electronics. So this is the electronics which is lying inside mounting board of IBC IPSP. So when you look at the physical MBM 120, you can see a lot of protrusion here, sheet metal work. Basically each one of them has their own purpose. So what you see here is locking lever of IBC, and then there are two locking slides of IBCs are there. These slides will be moving up. When you lift this up, then these will be moving up. And then there are locating pins. See, you can see here locating pins for IBC. It is having 3 places. So when the module is getting jacked in, that gets located. The connectors get located by this. And then when we lift it, then it makes the contact to this mating connector. And then when we release it, it's just a hook kind of thing. Then module is held in place. We should ensure that the locking lever is pressed down. So that is how the module is getting locked properly. Similarly, left side if you see, locking slide of IPSP is there. And locating pins are 4 numbers. And then this is the corresponding locking lever for IPSP. So this is quite, basically it looks very simple, but all these mechanical designs we have to take care when we remove the card and then jack in the card. So we should ensure the purpose of this thing, and then we have to take utmost care. The thing is the IBC will have the very delicate pins which will be used to connect to the inside circuitry in the MBM 120. So if you forcefully try to pull out, for instance, this locking lever is down, and still if you want to try to remove the card with force, then the module gets damaged and pins will get bent. So we should be taking care of the modules because they're very highly sophisticated design. So the complexity and the simplicity both have gone inside the module, and then module is miniaturized in the design. So accordingly, the module pins and the other things handling should be very delicate for IBC kind of modules. Next is here you see X12. This is the clip or lamella we call. So this should not, if it is, it should not be lifted up because this is inside the circuitry through an inductor. It's connected to 5 volts ground. So we should ensure when we remove the IBC, ensure that that doesn't, if this is bent or it is lifted up, through which it will form a path. I think one Mr. Shravan Babu has to mute, I guess, no? Some disturbance is there. You're muted, no? Okay. So this, let's get into the internal details of IBC modules. Basically, morning session you would have discussed AC and CS. How AC and CS, that is a processor module, gets connected to IO modules. AC and CS and IO modules get connected through IBC. That is basically through Ethernet link. So IBC combines PCS and IO units. And then PCS and FBC are the two software blocks inside the processor module. So this is for acquiring data, that is FBC. So all the IO modules will line up the acquired data to controller module through IBC. So this basic function is we have to give a connection path between processor and IO modules through Ethernet. That is FBC is the functional block inside. And further through FBC, whatever data is captured, that will get processed through PCS functional block. And that is on the upper level network. And lower level network, it has backplane bus, that is RS485 asynchronous 1.5 Mbps serial bus. Two redundant buses are running in the backplane between modules and IBC. Top level AC and CS, then through Ethernet it gets connected to IBC, then from IBC through backplane, IO modules are seen through RS485. So it can capable of taking care of 32 IO units and redundant backplane bus lines. And also there are two lines I2C buses running in the mounting board through which IBC reads its own, it gives the input for the regarding its temperature, that is inside the casing air temperature, and it reads the casing in air temperature of IPSP also. And IBC's address is set by S1, that is this switch. Here whatever we saw, no, S1 is the bottom switch. And also an FSFLT will be generated by IPSP, that is it will monitor the fuse of F1 and then it gives if this fuse is blown, then fuse fault will be reported to IBC. So it monitors FSFLT line generated by IPSP also. This is the internal structure of IBC. IBC comprises of two PCBs inside. If you see here, there are two connectors, no? This is from one connector from one PCB, the other connector is another PCB. So both PCBs are joined together by these connectors X5, X2, X18. So through which they are joined together and then by X1 and X4 they get connected to mounting board here. So these pins are only, I was telling it's very delicate. We have to handle it with utmost care. And A board we call it. A board is comprising power supply circuitry required for the entire board's operation. And then we have a Freescale make MPC8247 microprocessor and SDRAM and Ethernet circuitry and LEDs. Further, in B board, we have all the associated bus related signals. Like we have two redundant IO bus, I said SDRD-A and SDRD-B. Then after that, to look at the redundant bus, through redundant bus to adjacent group, IO group modules will be taken care by IOB bus. Then between two IBCs, master and slave bus, RMRS bus will be running. That will be through this mounting board Ethernet connector. See, we shouldn't get confused. Actually, module IBC will have one Ethernet connector on board in the bottom of IBC, that is shown here. Then mounting board through this IBC, this Ethernet connector is to get the connectivity from AC and CS. Whereas this one, IO lines, backplane IO lines, this gets converted and then not converted, it gets communicated to the adjacent group IO lines through this Ethernet connector. So these are the X4 will be connecting to MBM120 and these are the bus lines which will be going through X4. X1, IBC address is taken in, then temperature input I2C bus is running, then 5 volts and ground, power supply and its own ground and clock sync. This is for DI signals times in cup. And then fault line, FSFLT which is generated by IPSP that will be running in the taken inside the IBC. For that also one pin is there. So these are the functions of these X1 and X4. So if suppose X1 particular pin is bent, that pin is supposed to read temperature, means that is I2C pin is bent, means will not get the temperature of IPSP. So then it will keep on reporting IPSP missing. It is zero temperature and all such things. Then there may be some alarms and things like that. So pin bend will be having serious repercussions. And also certain lines which are used for IBC address is bent, means and by default it is logic 0 is taken and there may be some erratic behavior. So pin bends might cause a havoc. So we should take care very clearly. Then after plugging in the modules, we should use TST120 to check the integrity of the connections. And these are the front plate lines. So you can see here. So channel 1 and channel 2, if traffic is running in channel 1 and channel 2, so corresponding LEDs will be glowing. Then similarly here ION, this IO1, IO2, that is STRD-A and STRD-B. So TX RX lines, then RM and RS, that is master slave lines between IBC. So there are these LEDs. The purpose of the LEDs are this. Then run, when active ACN is connected, then run LED is up. This run LED is glowing, that means IBC is seeing some of the IO cards. Then when SBY is glowing, that means none of the IO cards are being seen by IBC. That's the meaning. Then if you see the rear panel of IBC, there are some piano switches. These switches are used for indicating the personality of IBC. So typically for IBC to work as IBC, we need to put 4 and 5 switches on. Addition to 4 and 5, 2 and 6 should be made on in case we use it for redundant mode. So almost all jobs which are executed by BHEL, they go on redundant IBC mode only. So ideally when we inspect before installing the module into the rack, for instance spare modules you are receiving. So before installing them into the rack inside, we should ensure that 2, 4, 5 and 6, they should be in on condition. That is push down. Here you can see here in switch itself it will be written on. So this one in initial slides we had discussed. This is IBC IPSP, one of the mounting boards which will be used for redundant IBC functionality. And this module IMBS 120 will be connected when we don't want IBC redundancy. But this is rarely it is getting supplied. But the purpose is same, like power supply wise and then this X12 wise, no, that purpose is same. This is used only in economy mode. You can see here it will be clear. See, typically all the panels supplied by BHEL, you will see this structure. So IBC and IPSP both are in pairs. So then we are supposed to connect the interlink cable here, and also there is another line for data redundancy. Here we have to put a Ethernet kind of cable. So then each IBC its own IO cards and adjacent rack IO cards. We call it IO stick, IO group A and IO group B. So this is the typical connections what you will be seeing in the panel. Suppose we use MBS. MBS is this module which we are not actually it's not in major supply. If we use this, we lose IBC redundancy. The same pair of IBC and IPSP, it is supposed to take care of 2 IO groups. Here 16 and here 16, total 32 modules it is supposed to take care. Of course, for this IO group to get the power supply, we should put the interlink cable which carries plus 5 volts. And the Ethernet cable which will be giving the data path for IBC to see these modules. And there may be some configurations where we want only IBC IPSP redundancy which will be looking at only one group of modules. It's the same bus but 2 pairs, redundant pairs. So in such cases both places MBM 120 we have to put. But typically this is no redundancy at all. It's one single IO group and then one single pair IBC IPSP. And this is the most widely used configuration here, right top. And this is just for the understanding sake. We have just taken a photo only when this mounting board Ethernet connector is connected. So this is a cross cable. So that will be connected when it is in redundancy. This is the power supply redundancy cable, that is interlink cable. 5 volts is being carried through this. And there's a slide switch which we discussed in the very first slide. So typically for redundant IBC IPSP, both switches should be made on. This is a recommendation. So MBM 120 plus MBM 100, there's a middle row. So S3A and S3B both should be on. Otherwise we lose the purpose. If you switch off, then even there is some problem with the connection of this power supply redundancy cable, this module will not give out an alarm to upper level side. The purpose of putting redundant IBC and IPSP is to get the alarm and then smooth functionality. Something goes bad, then the upper level system should come to know. So obviously then these two slide switches should be made on. So when you receive spare cards and insights, in case it has to be replaced MBM 120, then we should ensure that these loop control switches are made on before installing. Similarly, IBC backplane switches, we should ensure that 2465, they should be put on before installing the module into the backplane. Next is IPSP. IPSP's whole purpose is convert incoming 24 to 5 volts. Actually, the input voltage range is 18 to 32 and it has basically two outputs. One is 5 volts and the other one is 24. Another one is 24. But for M120 system, morning session you would have seen why we call it M120. That is basically 120 mm by 80 mm. That is the PCB size. So for these set of cards where they have channel to channel isolation in almost all modules. So these set of cards will not use the 24 volts which is the output of IPSP. So they use only the 5 volts. Incoming is 24, output is 5.3 and 24, but this output 24 is not used by M120. Isolation is 500 VDC between input and output. And startup is 21, shutdown is 18.5, and it has a temperature sensor inside the module. So the accuracy of it is plus or minus 2 degrees. And then it monitors the field supply. That is that whatever we X8, whatever 24 volts we connect, no? So that's getting monitored over here. And then there is an LED indication here. If you see incoming voltage is within the range, then this will glow green. Then output voltage is 5 and 24 both. Basically here what happens, incoming 24, then this 24 is generated. From this 24, 5 volts is generated. So typically working module will be glowing both 24 and 5. And if any of them, there's a pop-up, what startup and shutdown is for the module's functionality. There is a query somebody has raised. What's the purpose of startup voltage and shutdown voltage? That is the module electronics. See, IPSP will start working the moment it starts picking up 21 volts. And then if the moment it goes below 18.5, then it shuts down. But typically our input is from DC-DC converter and things like that. So that will be stable 24 volts. So that's the idea here. So if any of this input voltage and output voltages are out of range, so they will be, there is a fault LED that will be glowing here. So next is analog input modules. See, we have 3 varieties of analog input modules. The nomenclature goes like this. Here all analog IO modules are channel to channel isolation they are having inbuilt. Channel to, field to system is by default all modules. Over and above, channel to channel isolation is also existing in this set of modules. So we have 3 modules which are together designed similar PCB. Similar, same PCB is shared, but functionality is differing by signal conditioning circuitry. Bus AII8CN, that is analog isolated input 8 channel and current input. C is for current input. N is no sensor supply. Analog isolated input 8 channel current input and no sensor supply. And 8 channel, the same thing, second module is analog isolated input 8 channel current input That means this will be by default, it will be giving sensor supply. Next is AII8V, that is analog isolated inputs 8 channel voltage input. So these three are the group of modules, analog isolated input modules. So this is spec sheet. Measuring range is 0 to 20 or 4 to 20. Same thing for C and CN. V is 0 to 5 or 1 to 5. Input impedance is mentioned here. And what happens in AII8C module, there is a channel specific current limit. So the moment sensor draws more than 30 milliamps, then the current falls back. The module announces a fault condition. So this voltage supplies to transmitter. CN means anyway it's no sensor supply, and C will be always giving. So this is the range, minimum 21 volts and nominal 24 volts. All modules have 8 channels, and AD resolution is 16 bits. This is accuracy 0.05% at 25 and 0.01% per 10 degree rise. So for the entire operating range of the module, we might touch 0.1%, worst case. This is parameterizable software filtering. This is software settable. From the FB-CAD, we can just change if you want filter circuitry. But that goes as a template. By default, it goes from a template. The module design allows 35 milliseconds to 81 seconds. Measuring interval is scan rate. Once a module is called out, how much of time it takes to give IBC about all 8 channels data. That is 16.7. Isolation between the channels as well as isolation between field and system is 1.5 kV. Here also we have all three modules have two circuit boards, PCBs. We call it A board and B board. A board houses 3 channels and B board houses 5 channels. They are totally identical channels. And then in addition to this is A board is housing bus interface portion. That is system side, how it talks to IBC. So each module will have dedicated microcontroller IC, and then they have their E-square prompt to hold the calibration value, and then they have RS485 circuitry drivers for talking to backplane, because backplane will carry two RS485 asynchronous 1.5 Mbps line, which will be driven by IBC, governed by IBC. So then when it enters module, then this circuitry is coming. Then as you all know, module is location specific. So inside the rack, so where the module is placed, accordingly its address gets defined. So to get that address decoding, there is a small circuitry. Then for LED driving purpose, there's a circuitry. So these are all belonging to, then watchdog timer, of course. Then these are all belonging to system side circuitry. So this is the X1 and X2 are the connectors which will be connecting to backplane. So X1 is carrying fully system side, that is logic. X2 is drawing 24 volts from backplane. See, if you remember, we had discussed here X8 input 24, then F2, then X4 it is available. The same X4, it gets passed on to backplanes. And then when IO module is plugged into this backplane, X2 gets the same 24, and then that feeds as input to all 8 channels. But each channel has its own circuitry, isolator, DC-DC converter, all the circuitries are independent for all 8 channels. And then it gives out channel specific sensor supply. So this sensor supply and then this incoming 24 is totally isolated. That is how we get channel to channel isolation for all 8. And then when two PCBs are joined together, then this X4 and X6 and X5. So they will be connected together. And this X3 is the fields connector, front plate connector, what you see. Once you jack in the module through which IO connections are taken from field. This is a field connection drawing. When it comes to sensor supply, that is AI8C. On VS line, we have a current limiting circuitry for 30 milliamps. Then in the actual sensor current, field current, when it enters, then we have a filter. Then further it gets fed to ADC. Same thing here CN, but the thing is there is no, because it is not going to give the sensor supply, so there is no current limiting circuitry. The remaining portion is same. And V, actually incoming voltage, see this 249R through which this incoming current gets dropped and we get the corresponding voltage which will be sensed by ADC converter. But here input itself is voltage. Only after filled it directly just goes to ADC converter, ADC. And these are the connection drawings for field. AI8C, all three modules 2 pins per channel. A8C 2 pins means then one will be giving out sensor supply, the other one is taking in loop current. Whereas CN, the other that is common and the other one is loop current. Similar for V also. This is part of data sheet of course. So what happens here when it comes to channel isolation, there is some more pictorial representation. So C, when we take Vs, then this is last slide also we discussed this channel specific current. And then this 5 volts comes from the, no, this is direction is this way. This is what we get it from backplane field 24. And then we have an isolator fully through which we get 24 volts isolated. And then for each of the channels independently power supply is getting generated. That's how we get channel to channel isolation. Then similarly, this input side when it comes after filter ADC, then after that we have some isolators. So this data line and then converted data, basically ADC output and ADC control lines are passed through this isolators and then they talk to microcontroller because this side it stays in system side domain. So this is how the module isolation is taken care here. This is another island drawing just for understanding. So we have here totally 8 islands and then each of them are separated from a big island here. And AI8 module, all 8 channels will have front panel LED indication. So each channel is isolated. This already we had discussed. Yes, fine. And then this is a red LED. When all it will be glowing. See when there is a break between transmitter and the module. It's not connected. Then it will be glowing continuously red. Or short circuit also it will be glowing continuously red. See when communication between IBC and modules they get lost. Then all LEDs will be blinking at 1 Hertz. And suppose IO modules measuring limits are exceeding, then they will be blinking at 3 Hertz. This is the error reporting pattern. That is, individual channels will be reporting independently. That is one good design feature of these modules. Ideally speaking, when all modules are connected, all inputs are fine and they are operating within the limits, then we are supposed to see a silent front plate. That is, nothing should be glowing. So some communication problem means all will be in sync, it will be blinking, all modules in the rack. If IBC and AC and CS connections are lost, then all will be blinking similar pattern. Then one particular channel is broken and one particular channel limit is exceeded and all, only one particular LED will be blinking. That's at a faster rate, 3 Hertz. So this is the idea about front panel LED indication. So next is the cross connection board. So the CX59 will be used for AIA8V. CX59 is nothing but I to V converter, incoming current, then through a high precision resistor, 250R resistor, then incoming current will be converted to voltage. That is this direction. X11 is an incoming current. Then this I to V conversion, then output voltage will be available parallelly in X1A. One person has put up a question. In healthy condition, what will be the LED condition? That is, in healthy, it should be silent. It should be off. All of them should be off. So you can read here. It will be glowing continuous red when there is a problem, either open or short circuit, and it will be blinking in red when there is a communication failure or machine limits exceed. So when all are sitting in place, then we are supposed to see a very silent LEDs in the front panel. So incoming current, incoming current and then I to V conversion, then it will be available parallel. The moment it comes to voltage mode, then it becomes available in two parallel connector. So this is what you are seeing X11 here in the photo. X11, then after getting converted, then here X1A and X1B both will be available. Then from here one AIA8V and here another AIA8V redundant modules will be connected. This we consider as one group means then similarly one more group is there in CCB. So this is the functionality of CX59. We have a bridge rectifier, so reversal of polarity doesn't matter in this module for incoming current. Next is CX60, same fundamental of operation, but instead of two modules output side, we have three. This is for triple modular redundancy purpose. They would have used this. Some limited panels, you would have seen these cards. Incoming current, then output will be available in all three. This is the idea. Same set is available second time also here. Next is TS51. TS51 is TST120 module. This is basically a troubleshooting card. It doesn't get connected to field or something. When all the connections are made, then you can place TST120 in any one of the slots of MBI8. Now, before TST120, let us just go to MBI8, then we'll come back to. This is MBI8, MB51. This is the backplane module which will be housing 8 modules. So 8 modules will be housed in one module. So in a typical of one IO group, you will see 2 MBI8 connected together. So here for 2 slots, one slot is shown vacant. So remaining modules are placed here and then IO terminator is placed in the far end. And this bottom what you see is the field connector for DII8P24 model. DI cards alone will get the field supply from this bottom connector. And this module, when it is connected, no, then see if you see there are so many places where we have to meet the necessary connections. That is, first one is when we connect IBC to mounting board. That is the first connection point. Then after that, MBM 120 to MBI8. That is, wait 1 second. That is this connector, X4. If you see, we have put IBC here, then this module should talk to MBI8. So then here the second connection point. So third connection point is from this MBI8 backplane connector to module connector. Then fourth one, if the module is in the far end, first MBI8 to second MBI8. Then last connection is second MBI8 to IO terminator. So these many places we are supposed to see the pins meeting the adjacent connector and then we want to have a reliable connection. So once we have the reliable connection, then modules will aramse work. Most of in this set of modules, some of the problems what we have encountered, that is pin bend of IBC, that might cause a havoc. So whether we have connected properly, whether all the necessary connections have been made and signals are running to know that this test module is used. That is the purpose of this TST120. So here one more thing is this hex rotary switch is there. One switch you can see here. One person has posed a question. How DI card will get supply? DI card will have two portions. One is field supply, one is system supply. System side plus 5 volts come from this top connector. This is where whenever module gets powered up. But the field side contact interrogation voltage come from the bottom connector. We have to connect 24 volts here. From this, actually here it gets routed to another 2 pins here. Then only DI card will use that. Whereas 24 volts from MBM 120 whatever comes no after F2, that is coming here, and then they will be available in some other pins. There are several pins in this bottom connector. Some pins are allocated for this 24, some pins are allocated for this 24. Accordingly, the module will take in the 24 and then operate. DI ka AEF field supply. So this bus signals, address lines, 24 volts, 5 volts, all are from backplane bus. So 24 volts is here and then 5 volts is here. So this is how it is grouped. So here this hex switch is there. Whatever address we set, that will be the module address. See what address we are setting here into 2 plus the location of the slot. That forms the module address. So typically we will have two MBI8 connected adjacently. So first MBI8 we set 0. 0 into 2 0 plus 0, that is the module address of first location. And 0 into 2 0, 0 plus first location, 0 to 7, that is how the module gets addressed. So first location, second location, third location, like that. Then further how it is read, next MBI8 we will put 1 2 3, then 4 we will put. So 2 into 4, 4 into 2 plus module location, that becomes 8. So here 0 to 7 I2, then 8, 8 to 15 it will become. That's how the module addresses are getting taken care. Whichever location you put, that gets fixed. Module address gets fixed for that. So this is the purpose of MBI8. Now let's get back to our TST120. TST120, when we plug in, then we will see here there is a LED for bus 1A, 1B, 2A, 2B. So when all connections are up and integrity is maintained, then all LEDs is supposed to glow. 1A, 1B, 2A, 2B. Then 5 volts is fine. Then a 5 volts LED will be glowing. And 24 volts is, this is input to IPSP. So what is cause for LED being off is all the interconnections and then MBM 120 fuse F2 or input voltage 24 volts, not okay. Then there is a voltage called, labeled as 28. This is FPI, which will be connected at the bottom of the MBI8. So internal connections of IO group or MBI8 24 volt fuse field supply is not okay. In case we use here, whatever we supplied is contact interrogation voltage is only 24. In case there is a module variety which will use contact interrogation voltage 48. If you use that module, then we have to connect 48 instead of 28. 24 in the bottom connector. And bus 1A and 1B, 2A, 2B, these ones, all internal connections of IO group not okay. Right from IBC to mounting board, we have to start suspecting if these LEDs are not glowing. That's the idea. And one more thing, here if you see this also are connected to the second MB8. So both MB8 will have the bottom 24 volts. Okay. So one place if we connect, that gets carried to the adjacent MB8 also. So next is AOI4C. So let me just take 2 minutes break. Actually, there's a question from someone. AIA8C card 24 volts to field transmitter is from bottom 24 or MBM 120. This is from MBM 129 as a straight, because anyway it is not from bottom 24. Bottom 24 is only for DI card. So AI8C, what happens if you see, if you remember this block diagram. See, this is MBM 120 X4 connector, side connected 24 volts. After that, there is an internal to the module, there is a DC-DC converter, which will give isolated 24 volts DC. So that is getting connected to VS. This will be going to transmitter supply. This circuitry will be repeated 8 times inside the module. So we can't say this is the 24 volts which will be common for all 8 channels at input point. So this is a dependency is there, but this is not exactly what will go out. So this is internally one more 24 volts is generated in the module. That is what is going to, after this current limited circuitry, that is what is going to go to transmitter. Mr. Santosh, 1 minute. In AI8C card, all the channels show pink values. If you remove connections from one particular channel, all other channels show correct values. Why does this happen? What about front panel LEDs? You have any input? Front panel LEDs are off or all were red means totally it is shorted to some ground, no? That is the reason. One particular channel you are removing, no? So that channel you might have to inspect further. Is it random? No, any one channel if you remove it becomes alright, or one particular channel, sir? Then that particular channel has to be inspected in detail. Have you swapped the cards and then tried? For instance, the AI8C module from somewhere else you put in the same location. Is the problem persisting or it's going off? So yes, swap the card and then problem goes with the module or problem lies in the location. Whichever card comes to the location, is it behaving the same way? Or wherever this module goes, the problem is carried by the module. What was the observation? That means the card which is shifted from this location, that works fine in somewhere else, right? Yeah, replaced IO card. So that means it's not a hardware issue. That is, module is working fine in some other location, right? So you need to trace back through CCB or whatever it is. No, you need to trace back because it appears that it's a location specific. Whichever module comes to this location, the problem lies in the location, and then to be specific to the particular channel. So that channel wiring you might have to trace back. Because the idea of having channel to channel isolation is the error or problem in one channel should not affect the other channel. But what is the problem in that particular channel where it is shorting? If it is shorting to the, see, it depends on how it's done in MCC also wiring. So whether in that place, then all the IO channels, module gives out independent lines, independent two lines per channel module gives out. But final wiring, how it has happened, you might have to investigate. If in the final wiring, if you're shorting all the return path, then some particular channels problem will be affecting the other cards also. You're from which site, may I know? This is Nalco. Okay. Please try that, and then if the problem persists through CE engineering, corresponding CE people, then you can approach module group. Because what I see here by your response, the problem is not lying in the hardware of the module. The problem lies in the wiring side, I guess. So you can just check up with, after trying out what I said, you can check up with CE engineering, and then they will refer to us in case further hardware problem is suspected. So next question by Mr. Santosh. If DI card is replaced with AI, then from where supply fed to that? That is from the bottom connector, of course. You cannot just like that replace. See, the typically DI card means field supply has to come from the bottom connector of MBI8. All other cards derive their field side circuitry के लिए power supply. It's not only sensor supply. If you see here, for the channel circuitry to operate, we need +10, -10, +5. Everything gets generated. independently. All these are from MBM 120 24 volts. Is that clear, sir? Yeah, it is okay because the run LED means that IO cards are speaking to that particular IBC. When SBY glows, none of the IO cards are speaking to that IBC. Through none of, see, there are two redundant instances. Inside each IBC, there are two redundant instances, software instances. So none of the cards will be talking to those two instances of that particular hardware IBC, then SBY glows. So showing run LED status at the same time is fine because some cards in that particular rack will be talking to IBC in one path and some other cards will be talking to the top IBC in one path. That is why we see both run status. Okay. And by the way, what is the IBC version you are using, sir? You have that input? If you have, you can just key in. We'll further discuss. Okay, next is AVO card. AOI 4C. We have only current output variant of analog output module. AOI 4C and AOI 4H. One is for current output, one is current output only, but with hard capacity. Y'all, anyone is using, I don't know, the participants group, whether, okay, we don't know whether hard card is used or not. Let me cover in any case. Okay. So number of channels are 4. Unlike AI is housing 8, AO is housing 4. Output range is 0 to 20 and 4 to 20 depending on the template configuration. So 750 ohms, more than that if it sees the line resistance, it's break limit. Then accuracy 0.1% at 25 and 0.001% for each 10 degree increase. Overall it will come to 0.15. Worst case. DA resolution, DAC resolution. See, in the case of analog input model, we had ADC, analog to digital converter. In the case of analog output model, so ulta of a digital to analog conversion we will have. Because processor will be writing the digital data, IBC will be passing on to this module processes it and then converts to current and then sends to field. So the accuracy is 14 bits, resolution is 14 bits, update interval is 5 milliseconds. Isolation is the same like AI, 1.5 kV. This is a functional block diagram. So here also same funda, A board and B board. A board and B board. A board has a system side circuitry and 2 channels. And B, this particular one, top one if you see, that is AOI 4C. Okay, bottom 2 drawings are corresponding to AOI 4H. So basically when you open the modules are housed inside the plastic enclosure, as you all know. When you open the card out, after taking out this plastic enclosure, the card to card connector has to be just separated. Then you see this layout. So 2 channels on A board and 2 channels on B board. And X4, X8, X6 are card to card connectors and X3 is field, which is highlighted in green. Green is external connections. X1 is top connector, system connector for MBI8. X2 field supply connector. And this portion is same like AI only. So CPU takes care of IO communication, that is bus communication. All other points remain same. And then similarly here if you see hardboard what happens, there is a separate CPU. This CPU, main CPU is for normal communications, normal data from IBC to IO modules and further to all channels. And then here hard CPU, what happens, it takes care of only hard traffic. And then that's a dedicated CPU here. And then hard CPU, then its own UART also is there, that is universal asynchronous receiver transmitter. So a lot of hard data will come, so that gets communicated to the channels through UART. So that's the difference, basic difference between internal difference between C and H. So here the interpretation of front panel LEDs, AOI 4C, if you see continuous red is resistance too low. That means we need to have some minimum load, so that is not met, means in continuous red, and blinking pattern is same as all modules. 1 Hertz communication failure, 3 Hertz, there are some measuring limits are exceeding. Here in this case resistance too high. In addition to the same blinking pattern, for heart module, yellow color also is defined. So if you see here only red is shown in the front panel LED, only that color is defined over here. Whereas in heart module, red and yellow both are defined. So when yellow will be glowing is there is some heart packet which is getting transmitted and received. Heart up and down means we will be seeing blinking yellow in between. So when module works fine, then we are supposed to see a silent front plate, that is no LED glowing, and only for heart card once in a while yellow blinking will happen. And these are the IO channel connections. So odd pins are carrying return path, even pins are carrying the output current. This is the functional block diagram, the channel side. So this is incoming digital lines. What current value has to go to field, that gets converted to analog. Then further for current generation circuitry 4 to 20 milliamps is there. Then with additional protection, then it goes to out. And here whatever current gets generated here, depending on the digital value, it gets read back. It's read back by ADC, another ADC in the return path. And then it constantly gets verified to the control circuit, whether what is being written and what is being read the same or what. So then finally it gets a clearance. So that means readback option is there for analog output. Then the value goes to the field. So this for heart side, okay, corresponding amplification circuitry is there, then heart signals are going. And there is basically heart modules will have a modem housed in the PCB. Modem, and then for the modem to operate one more separate oscillator, and then UART and dedicated CPU. This much circuitry extra will operate for heart. This is the same island drawing what we had seen in AI8C. So these 4 independent islands, and then they are together, they are separated from the logic island. Then YXR16AO, this is a cross connection board for AOI4C and AOI4H. Basically this is the field connector, and here the processes modules will get connected to X1A and X1B, and then through the decoupling circuitry present in the CCBs, then this module goes, current goes to field. Here in this case the design is redundant AO modules, both will be giving a current output. Okay, and then through the circuitry which is present inside AO module, then 4 to 20 milliamps will be flowing out to the circuitry. If you all are anybody had worked on Max, then you will know clearly. Max there is only one, depending on the personality of the module, there's only one module which will be giving out loop current. Here, when both modules are fine, they pick up the return value, converts, checks, and then gives out to field. Both modules will give out. And here, because of this decoupling circuitry, then finally 4 to 20 milliamps will go out. Similarly, one more set is available. That is all. And here this we discussed, MBI8. Then next is temperature input modules. What all we had finished is analog input 3 modules, analog output 2 varieties, IBC, IPSB, then IBC, IPSB's mounting board, then module mounting board, then TST120. This much we have done. Last bunch is temperature units, M120 temperature units. We have a specific unit for the thermocouple input, that is 8 channel, thermocouple input, that is TCI8, thermocouple ICE input, 8 channel. These are all channel to channel isolation is present. Then 2 wire connection. Then these are the list of thermocouples which can be supported is mentioned here. And TIA4W3, TIA4W4. That is temperature input. That is RTD input cards basically. Temperature input isolated, and then 4 channel and 3 wire. That is TII4W3. Then temperature input isolated, 4 channel, and W4 is 4 wire. So 4 channel temperature input units, PT10, 100,000 are supported, and 3 wire or 4 wire connections. We have a separate hardware type for 3 wire and 4 wire. Somebody has put some question. Break limit. Which resistance? That is wire and load both put together. If 2 cards measure different values in tracking, then what might be the output? 2 cards measured different values in the sense totally different values, sir. But we have know what is a known good return value that will be known to the module by reading back. So the other module which is totally away from what is the return value, that will not be considered as a healthy output. No, it will be tagged with a fault bit also. So that particular module's output will go, and then obviously with the fault bit card, fault bit whatever output comes, that doesn't get considered. Different values means to which extent different values you mean? See, for instance, 12 milliamps means 12.005 and 12.004. That is because of the very minor differences means it goes the higher value it goes. Suppose 12 milliamps is written, then one module is, it can't convert it. Return value only will get converted because of some hardware problem. Okay, 5.2 and 5.4. 5.4 only will go out. You are facing any issues? 5.2 and 5.4 both will be tagged as healthy. That is correct, no? Why and how, that is depending on the circuitry inside the CCB, sir. The higher the one only will go. Are you facing any issues because of this? Five point one, 2 and 15. Then you must check whether which channel reading is without fault bit. Are both of them without fault bit? Then configuration also needs to be checked whether they are connected as redundant IO block. All those things come into picture. And have they written the template as retain the old value? Suppose communication is lost means we have an option whether to reset the value or retain the old value. All those things, how it is configured, we have to see in case both channel outputs are tagged without any fault bit. Because there is a block called RIB inside FBCAD. That RIB block, we cannot split and treat the modules separately. The RIB block treats both the modules in the redundant channel circuitry as a single entity. You must be aware, no? RIB will have a address location for primary module and then secondary module in a single block. So you can't separate out redundant cards. So if you are facing like this 5.2 and 15, you must really check whether are they with or without fault bits, which channel. I think I suggest you to discuss with C engineering for this case. Then one more thing you had asked. Okay, this I had answered. Which resistance limit? Break limit. That is including load resistance. It is. Here it will look for a minimum load resistance also. That's what I mean. That 750 ohm is maximum break limit. But simply if you put a multimeter, no, in the analog output module, it will not read because it will be looking for a minimum load resistance depending on the template values. So then accordingly you have to connect a series resistance, then only module will read. But in template, if they maintain that 0 is the minimum load resistance, then it will measure the current. Okay, fine. We'll move on. Then M120 temperature units. CCB output is 16 milliamps irrespective of input. Then did you check at the analog output module, sir? You can unplug, no? In CCB, you can remove one module and then you can check in the pins, no? In X1A and X1B, one of the connector you remove and then measure the CCB output. Okay, whatever you are writing, if it is available in the wire end, then obviously in both the wire ends, that is X1A and X1B, that is one way of troubleshooting. Because we have to isolate, no, whether it's a CCB problem or it cannot be CCB problem, because CCB will not have any intelligent circuitry. It just routes what comes. So irrespective of input means you must be suspecting one of the redundant IO cards. So that's what I am saying. Whether if you see run a test mode in that FB CAD, you will know clearly what is written and read back is same or not. If read back is not same as a return value, that there itself it will put up a fault bit. Okay. So M120 temperature units. This introduction is done, and then here these see here one more thing is the linearization. Other analog input cards we have just y equals mx plus c, that's a very linear curve, but whereas temperature cards there will be lot many levels of linearizations which will have to happen. All these linearization related calculations are residing in controller modules. So here type of RTD which is connected, and then what is the type of output, that is all it is seen. There's nothing the module processes for linearization. And there is a very big table over here because there are several, as you know, the RTD elements, depending on the elements, then the accuracy and the resolutions and things like that will vary. And here one more thing what they have done, unlike analog input modules, see that we know the clear cut range in the analog input model, 4 to 20 milliamps, that's at 4 to 20 milliamps. Here it varies depending on the RTD type and depending on the thermocouple type, because ranges also vary. So accordingly our requirement for analog reference IC which is inside the module will be varying. So they have picked up an ADC which has programmable gain amplifier. That is a multiple options are there for different gains. The ADC picks up different value and then converts the incoming signal. For instance, the range is very small. Such an element if it is picked up, then obviously this gain of this inside ADC, that will be programmed as bigger gain, so that the conversion becomes easier and smoother, the curve becomes smoother. So that's why these cards are little sophisticated temperature input cards, because of PGAs what they have used inside. Otherwise they are very quite stable cards. So this bus interface portion remains the same, just like how we discussed. 3 plus 5, that's the channel organization. And both TI4 variants, they share the same PCB, 2 plus 2. Only 4 wire and 3 wire, there are a small circuitry differences in the signal conditioning side. Some resistance and capacitors are different. The blinking patterns are same, just like our what do you call, analog input modules. Continuous red is no connection or short circuit. Blinking pattern is same. And here one more thing, what is break fault limit? Which modules are this is? One Mr. Suryakanta Mahapatra. What is break fault limit means? Which module you are talking about, sir? You can just key in that module type. Thermocouple. Break fault limit is break monitoring limit. Is this what you are meaning? That is more than 1 kilo ohms, then only it will be considering as actually the wire break has happened. That's the thing. And here once again, if the line resistance is more than 1 kilo ohms, then only this line is considered as broken line, that is break monitoring limit, that is. And here the cold junction compensation, that is not a part of this particular module, like max TNA. Max TNA, when we pick up thermocouple modules, there will be on top and bottom, there is one small connection where we can connect that temperature sensor for CJC. Here we have to configure one more TIA card, one particular channel for CJC, and then it has to be taken as a calculation inside the system configurations. This one TI card, RTD card, we have 2 LEDs per channel. So here 2 different colors are defined. So continuous yellow, because continuous red is break in the field circuit or one of the lines. See here, what is the difference between 3 wire and 4 wire? Monitoring current is passed on to the sensor through plus in the case of TIA4W3. In the case of TIA4W4, monitoring current is sent in a dedicated line. If you see here, TIA4W4, IM0 is going on a separate line. Whereas W3, IM0 will be sent on this plus itself. So break in any of the field connections, IM0 or C, that is common line, any of the lines. Then this comes as a continuous red. Then continuous yellow is measuring limit range is exceeded. So these are the internal channel descriptions. If you see TCI8, whatever I mentioned, PGA, programmable gain amplifier. So incoming thermocouple signal, then after filtering, then inside ADC, whatever PGA is there, that is scanning what is the incoming type of signals. Then accordingly, depending on the program inside the module, not no, it's a module firmware. Then accordingly, the gain is picked up and then amplified and then converted and isolated and given to the microcontroller. And time to time for monitoring the line, then there is a open circuit test pulse is being sent on this line. So if the circuit is getting close, then we will get a corresponding value here. Time to time it is being sent. That is the reason we see. I think can somebody is not muted, I guess. Who's that?
చెవులో పడిపోయి మనం మాట్లాడింది వినపడుతుందా వినపడతా అన్నిట్లో ఉందిగా
Okay. Next is TI4 and W4 also similarly. But here the monitoring current varies depending on the type of RTD which is selected. If it is a lower range RTD, then we will be sending 1 milliamps. If it's a higher range RTD, 10 microamps. Depending on the RTD sensor type, then different sensing current is being sent to get the proper response. So this monitoring current, in the case of 3 wire, it is sent through this positive only. In the case of 4 wire, it is sent in the IM line, that is monitoring current line. That's it. And then this is the mounting board 24 volts. As we discussed earlier, this gets isolated and we get a separate 24 volt isolated line. Then further through the internal circuitry, we get 5 volts, which will be used for that particular channel operation. Similarly, here also the same thing is happening. Choose the island diagram. It's the same value, 1.5 kV. So with that, it gets completed. So any other questions? Can discuss, otherwise close.
అయిపోయిందంట క్లోజ్ అయిపోయిందంట అంటే ఈ సెషన్ బయట తెచ్చుకుంటే మంచిగా
So Padma ma'am, or you will be coordinating, ma? Are we? Somebody has written something. Are we going to get today's slides? Of course, all the training modules will be having these slides. Anyone, any other questions, or we'll wind up, sir? The someone I think is trying to ask something. What is this breaking? Or you can just type in comments. Who's Mr. Shall we wind up the session or you just find out?
నా బుక్ డైరీలో బండిలోనే ఉంది. నాది అన్లిమిటెడ్ కదా డేటా. అన్లిమిటెడా?
Any more questions from participants, please? Any more questions? You can post it off chat also, or you can raise your hand and ask through voice. Kindly come up. Any more questions? Swati, are you able to listen me?
అన్లిమిటెడ్ ఆఫర్కి అట్లా అన్లిమిటెడ్ వస్తుంది.
Yes, madam.
Okay. I think all questions are asked on chat itself, and they are satisfied as of now. And definitely, a lot of people have asked that whether we will get these slides and all that. Yes, definitely, we will share it across DHL file sharing system. We are collecting all the slides from our faculties, and we will pass it on to all the participants. Once we collect all the slides together, we will post it on the web, DHL web, and you can collect it also. So I yes, please come up, sir. Please come up. Any question, please?
Yes, can you please explain how the overall connections are done, starting from the IBC to SCN? We just went through how the IO modules are connected to the SCN or IO modules are connected to the IBC. So, can you please explain in a single picture that how the IBCs are connected to the SCN and how the IOs are connected to the SCN? Total connection.
But was it not covered in the general overview, sir? Morning session?
Actually,
Very first session. Didn't they show the circuit? I mean, connection drawing overall?
this is there we can that was a overall drawing, but without detailed connection we needed.
See what happens, no? IBC, ACN, I don't have a drawing here. I can just explain to you. And if it is anything not falling in line, you just let me know. Whatever we
Okay.
discussed in the morning session. See, ACN has an Ethernet port, okay, that we call it as FBC. Okay. So if you see each of the FBCs from ACN CS, that goes to IBC onboard Ethernet connector. If you see IBC module, at the bottom there will be two Ethernet connectors as it connected to the panel, no? So ACN CS to actually through the switches and all it will go, but I'm just telling you physically finally where the signals get connected. Because inside the panel, if you see from IBC, all will go to one switch, and then from the switch it will go to ACN CS. Okay, Ethernet switch. You must have spotted there. So then ideally the signals travel from ACN FBC switch then to IBC onboard Ethernet connector. Okay, that is called upper level network. Then IBC and IO modules, they speak to each other by backplanes. Okay, that is backplane. There is no wire connections over there. By connecting two meeting boards laterally, no, side by side, then these RS485 buses are getting connected to IO modules. So IBC talks to IO modules in RS485 bus. IBC talks to AC and CS in Ethernet bus. Okay.
Okay.
This is how the signal flows through.
Yes.
If you are having redundant IBCs, then you have like I had explained here, no? See 1 minute. Are you able to see my screen even now, or it's stopped?
Yes. Yes.
You are able to see,
Yes.
no?
Yes.
1 second.
Yeah. Two IBC connections you showed previously.
1 second. You are able to see this, no? Like yellow cable.
No.
No, 1 minute.
No. No. I can't.
Now, yellow cable. No.
No. No. The slide is fixed at the MBM 120 diagram.
Okay.
Yes.
Now
Now
you
I
are
can
able to
see.
see, no? So that yellow cable, what you are seeing, that is the data redundancy. Okay. So top IBC sees the bottom IO cards through this yellow cable. You got it, no, sir?
Oh.
And
Yes.
also each AC and CS will have two redundant FBCs and things like that. It has multiple paths, IO modules to reach IBCs. One is through the backplane bus, one is through the upper level network itself with that other FBC, redundant FBC, AC and CS also will be feeding in the input about the modules. There are multiple paths. Okay. Connection wise, these are the connections. Backplane is one thing and Ethernet thing is one thing. Another thing, because if you see IBC has two Ethernet connectors in the bottom. Okay. So both will be connected to one main switch and one redundant switch. Okay. So depending on the modules will be speaking to redundant ACN independently through the switches also. So redundant, when the moment it goes to other IO group, then there are multiple paths from redundant ACN, redundant switch, and then it goes to redundant IBC also. And then through the backplane also. That way it is structured. It's quite complex actually, redundant communication.
Okay.
Okay. Then next, anything else or we'll wind up?
Okay. Thank you for now.
Yeah. Thank you. So thank you all. So it's such a long session, basically 1.5 hours. So thanks for patiently listening and paying attention. So please take care of this IO modules and IO cards because pins are very delicate and then very, very miniaturized. So many of the issues what we have faced is due to handling of the cards. If we take care of that after putting the card and then checking with PST 120, almost 90% of the problems we can come out of. At least as far as hardware related problems are concerned, I'm saying. That's it.
Thank you also, Suja ma'am, for having delivered such a good lecture and in-depth topic about the digital cards and processor modules and other things. And you have also asked, answered other questions which are raised by participants. And I equally thank our participants also for having listened for a long time and paying the attention so much. And hope this is definitely adding to your site values like site knowledge and all that. So hope to see you tomorrow at 9:30. The session starts sharp. Kindly join online, sirs, please. Thank you. Stay safe. Good evening.
Okay. Thank you all. Thank you, ma'am. Thank you, Padma ma'am.
Thank you, ma'am. Thank you, Sujata ma'am. Thank you, Swati and Nagaraj Ramchandra, for having supported me for this good session.